Okay, this is our fourth segment on electric current, which deals with using a diagram to help us make sure we're confident in what's happening to the potential as we go around an electric circuit. The diagram on the right there gives us a maximum point for this particular situation of 12 volts, and we're just going to match up the letters over here with the various potentials. And again, potential in an electric circuit is measured in volts, so its symbol is V and it's measured in volts. It gives us a measure of the energy that's available per charge as we move around from point to point in the circuit. It's going to have, again, an analogy with gravity. The stair analogy is a good one here. We're first going to lift the object up to a new height in terms of gravity, and then we're going to let it fall, and we'll look at how it all goes around as we go around the circuit. Okay, so we're starting at the negative terminal, and the reason we start at the negative terminal is that's where the electrons start, and that's where they have the highest potential. Now, as we move through wires, that would be like moving along a level of a stair. You're not really changing the potential with respect to the level of height, which is equal to 0 down here on the ground. So both point F and E are essentially here at the highest point. Now, in reality, some potential is lost as we go through the wires, but we're going to assume for now that they are perfect conductors, and we're not going to get worried about how much they change because it's very, very little. Okay, the big potential changes really happen when you see energy being expended. In a light, if we light the light bulb with our battery, then when we go from point E to D, we're definitely going to be using up some of our potential energy, and therefore there is going to be a delta V, a potential difference. Now in this case, since we're using up our potential energy, our new potential will be less than it was before. So as we go from E to D, we're going to get to a lower point. Now I'm going to have it about halfway, and I'll talk about that as we finish up here later on. So over here in the stairs, that would be like now we've come down one stair. Okay, now it's a long stair, and the stairs in the stair analogy don't all have to be the same height, but that's our first stair. Now we go from D to C. Again, we're in a wire. So again, we're assuming that the resistance of the wire is essentially 0, that there's really no major work done, no useful work done there that we're going to worry about accounting for. So in going from D to C, we're really not changing anything. So D and C are really at the same level of potential, whatever that might be. So again, in the stair analogy, it would be like we had here was our object. We lifted it by doing work to a brand new height. We let it move over here. It didn't really require any work to do that. And then we let it fall, and as it fell, it would give up some of its potential energy to move to that new point. Now again, notice that's a fall or a drop. So we talk about this delta V over here as being a voltage drop, or a potential difference drop, or a loss of potential. Okay, now as we go through light bulb between C and B, we're again going to see energy being given off. Well, that energy had to come from somewhere. It came from the energy stored up in our electrons. So we're going to lose energy to that point. Now, how much energy we're going to lose? Well, if you think of what the potential here at the plus sign must be, the electron starts out here at the negative with maximum potential. By the time it has gotten through the circuit, it must use up all the potential that we gave it. So the potential here is going to be 0. Now, since these two are in a wire and they really don't create any change in potential, that means by the time I get to point B, I must be at 0. So here's point B. And then from A to B, I really don't have any significant change because I'm in a wire. So over here in the stair analogy, it would be the same as now we have fallen. The object has fallen all the way to the ground. It's on the ground, so its height is 0, so it has no potential energy. In order to make it go back up again, we're going to have to lift it and make that happen. Now the job of the battery is to take that 0 potential and through expenditure of its own energy, and in a battery it would be chemical energy, it'll use those chemicals to lift, to increase the energy, and therefore increase the potential of the electrons as they go through. So again, it would be analogous, it would be similar to taking an actual force and lifting it back up. Now you notice in my stair analogy, if I kind of connect these places together and I have a force that pushes up here all the time, that ball is just going to go, that rock is just going to go up and down the stairs. So same thing in a circuit. As an electron leaves the negative terminal, it will expend its energy as it goes through. The electron itself is not expended, just its energy. So when it re-enters the battery sometime later, it will then be re-energized in the battery, and then it will go back around the circuit again. And that's just going to be a continuous round and round motion. It's one of the reasons why we call it a circuit. The simple word for circuit is just to go around from the same place to back to the same place. You see the potential diagram here looks very similar to a set of stairs. So it's kind of, just I drew the movements on the level places to the left instead of drawing it to the right because I didn't want it to look exactly like the stairs. But really, you can draw it the other way and make it look exactly like a set of stairs. So in terms of the amounts dropped, I just wanted to make, there's one major rule that will be very helpful going forward. Anytime you go around a circuit, anytime you go around one complete loop of a circuit, all of the potential energy that you put in, all the potential gained inside the battery, has to be used up by the time you get back to the other terminal. So this was a 12-volt battery, so this potential rise was 12 volts. That means by the time I got done, I had to be back to 0. That means in the two light bulbs, I had to use up a total of 12. Now, since the two light bulbs look very similar, I made the assumption that each would take about half of the delta V, the change in potential, therefore the potential difference. Since the total potential difference between 12 volts here and 0 volts here is 12 minus 0 is 12 volts, I assume they would both use up about 6 volts. So this line right here would be at about 6 volts. Now, that's an assumption I made based on the pictures and everything else. In terms of an actual circuit, it really will depend on what the objects are. An object that is harder for an electron to get through will use up more of the energy. Just like if you're trying to get through an area where there's a lot of mud, it's going to be harder to get through than if the ground is nice and dry or you're walking on pavement. So there's a lot of connections between the mechanical world and the electrical world here, and we can use a lot of analogy to help us out, and it's really a good idea to do so because electrons and electricity you really can't see, but mechanical world is something that's around us all the time. Okay, so we're done with potential and potential difference. Just trying to get their overall concepts. They are extremely important. If you have a good grasp of how they work and what parts of the circuit they provide, it'll make your study a lot easier. If you never really get a good feel for what it is, most of what we do going forward is just not going to make any sense. So take the time to make sure you have these concepts, and if you don't, come see me. We'll go through some stuff. I'll try to help you out with the ideas. Okay, so when you come in, you should be building and trying to figure out how to make your light bulb light, and then looking at the parts that are necessary for any electrical circuit, and that'll allow you to then step off and go on into more difficult circuits. And that'll do for today.